welcome to ICANX Talks. I am Lan Fu, and a professor from Australian National University. Today is our ICANX Talk 139 and the second talk of April. And as usual, we'll have our speaker, Professor Feng from Tsinghua University, to deliver 1 hour talk. And then we'll be joined by our panelists tonight, Professor Shan Huang from Tianjin University, Professor Xiaoshen Zhang from University of Electronic Science and Technology of China, and also our ex-challenger, Chuanzhen Zhao from Stanford University. First, it's my great pleasure to introduce you our speaker tonight, Professor Feng from Tsinghua University. Professor Feng is a 973 project chief scientist, currently also director of Flexible Electronic Technology Laboratory of Tsinghua University. He's also the president of Zhejiang Tsinghua Flexible Electronic Technology Research Institute. Professor Feng's research is on solid mechanics and flexible electronic technology. He has published more than 260 SCI papers, including many in natural materials science advances and also advanced materials. He also holds 190 national invention patents and 9 software copyrights. He has won numerous prestigious awards, including the He Foundation Science and Technology Innovation Award, China Youth Science and Technology Award, National Outstanding Scientist of Science and Technology, Qiushi Outstanding Youth Award of China Association of Science and Technology, etc. And being ranked in first place, he has also won the first prize of Beijing Natural Science, the first prize of Technology Invention of the Ministry of Education, and many, many other awards. So Professor Feng, now the floor is yours. Please go ahead to share your screen.
Okay. Hello, everyone. First, many thanks for Professor Fulan's introduction. Also, I gratefully thank Professor Zhang Haixia to invite me to give a talk today. Professor Zhang Haixia established a very brilliant platform for us. Today, I will give a talk on flexible integrated device from design, manufacture, and application. I will give this talk following this outline. There are 4 parts. First, I will introduce the background and the motivation. So for the flexible electronics, actually we knew the concept and the definition of the flexible electronics. So the definition is is to integrate the different materials and the functional components on the flexible substrates. Therefore, they can form in the flexible integrated device. So the device and the circuits and the microsystems is flexible and stretchable. So we know the traditional electronics is rigid and bulky. It's not easy to deform. So, but for the flexible electronics, it's flexible, stretchable, and especially we can integrate the different components. For example, we can integrate the photoelectric sensors. We can integrate the MEMS sensors, and the most important, we can integrate the different chips onto the substrate. Therefore, the flexible electronics, in another word, is a microsystems, is an integrated devices. So it's powerful. So for the flexible electronics, it's very powerful and important. And its application is very wide. For example, it can be used for biomedical engineering. So we can, because the tissue, the organ of the human is soft is flexible. So the flexible electronics is naturally integrated with the human body. So also the flexible electronic can be used for wearable electronics. So human can wear the circuits, wear the communication systems. The flexible electronic can also be integrated with the platform. For example, it can integrate with the airplane. So in another word, flexible electronics is the interface between human, machine, and the cyber. So it's a bridge of the human-machine cyber integration. So for the flexible electronics, actually, the development of the flexible electronics has a different stage. So for the original stage is the scientists focus on to develop organic flexible electronics. So the scientists want to find some organic semiconductor because the organic semiconductor is intrinsically flexible. So if we can fabricate the device by the organic semiconductor, so the device is naturally flexible. Such as Professor Bao Zhenan in Stanford, Professor Huang Wei in Northwestern Polytechnic University. This research group put much efforts to develop organic flexible electronics. So in about 2000, around 2000, Professor John Rogers and Professor Yonggang Huang from Northwestern University, they tried to develop a flexible device based on the inorganic semiconductor materials. So they introduced some new structure biomechanics to design the electronics with the flexible and the stretchable. So now from 2010, I lead my group to develop flexible chips, or in other words, flexible integrated device. So we want to make the chips, make the integrated circuits as flexible and stretchable. So if we can make the flexible chips, so that means we can make our cell phone, TV, our laptop, every electronic systems into flexible and stretchable. So, but now, so flexible integrated device is the core of the electronic system. However, it's very difficult. Now, many scientists made much efforts in this area. For example, now we can realize a flexible display for industrial applications. Now, our cell phone display is used as an OLED display, so it's flexible. Now, for some flexible sensors, some kind of sensors can be made by the flexible. But now we cannot make the battery flexible for industry. For flexible chips and flexible microsystems, my group working on this area. So for the integrated device, so the definition of the integrated device, that means we can integrate a different unit into one chip. So this one chip has some function. So this is a chip. But usually the traditional chip is, for example, based on the silicon wafer. So we have grew some thin films on silicon wafers and then etching the different films into the unit, and then finally we can get the chip. So we can find every layer of the chips is rigid. That's why the chip is rigid. So for our object is to make the chips flexible and stretchable. So actually, we know for the semiconductor development, we have the roadmap for the integrated device. Now we list the flexible chips into the roadmap for the integrated IC, because now we know the more law. Now for the more than more law, we want to integrate the different function device or functional unit into the system. For example, we can integrate the MEMS, we can integrate the RF and another unit into one chips. So the flexible electronics naturally has this function. But we know if we want to make the integrated device into a flexible and stretchable, there are many challenges. For example, for the traditional chips fabrication, we know the process flow of the IC technology. For example, the first is the design. We usually use the EDI software to design the IC. And then for the fabrication, we grow the thin films and we use the lithography to etch in the unit. And then we use the package. And then finally we can get the chips. And then we also develop some testing technology for the reliability. So if we want to make the chip flexible, we have to answer these questions. The first is how to design a flexible and stretchable circuits. The second question is how to remove the thick substrate, how to make the wafer flexible. The third question is how to transfer a very thin, a flexible unit onto a flexible substrate. The fourth question is what's the failure mechanism of the flexible integrated device? So these questions lead us to find some approach to solve this problem. So, for example, for the first challenge, how to design. So for the conventional integrated device, it's rigid. It cannot be stretched. That's because the material of the silicon low fracture state. So however, for the flexible substrate, it can be stretched more than 15%. But for the silicon, it's more than 1% strength that will be fractured. So we can use another idea to design the device. So the material is the same. We don't change the material, but we can change the structure. For example, for the steel is very rigid. It's not easy to bend, to stretch the steel. However, we can use steel to make the spring. So the structure is different. So for the spring, we can stretch it, we can bend it. So this is our idea. We don't change the material. We don't change the inorganic semiconductor materials. We still use the silicon as a semiconductor material. We also use the CMOS process flowchart, but we can change the structure. So then we can make the chips into flexible and stretchable. So another challenge in fabrication is for the chips, we have to develop the wafer level manufacture technology, because for the chips now we have to develop the technology compatible to the CMOS technology. So, but for the wafer, so the wafer is very easy to damage during the process. So we know if we want to make the object flexible, so from the mechanics we can make the objects very thin. So if it's very thin, for example, for the table is very the table is made by the wood. It's very thick, so it's not easy to bend. So, but if we make the table very thin, so it's very easy to bend. So this is flexible. So for the wafer, so we can develop some technology to reduce the thickness of the wafer. So then the wafer can be flexible. So this is our idea to how to make the wafer flexible. So then if the wafer flexible, we have to cut the wafer into different chips, the die. Now we need to transfer the die or pick the die onto the soft, flexible substrate, and then integrate these chips, and then we package. So then finally we can get the flexible chips. So how to pick up the flexible chips, and how to print this software, these flexible chips onto the soft substrate. So we have to develop a transfer printing technology. This transfer printing technology is kind of pick up the technology. So for the last challenge for the flexible electronics, for the flexible chips, is the reliability and the testing. So we know the chips in our cell phone, in our laptop, is rigid. It cannot be deformed. But for the flexible chips, it's very easy to deform. We can stretch it, we can bend it. So it's very easy to fracture. So how to design, how to evaluate the reliability and the testing? We have to develop some technology to realize this. So following this outline, following this idea, so we developed the design, we developed the fabrication, and we also show the applications by medical and engineering applications. So the second part, I will introduce the design and the optimization. So I just introduce our idea. We don't change the material, we just design the structure. So the first to change the structure is for the interconnects. So for example, for the steel, just like the steel, I just do the example. The steel, we can, it's not easy to stretch, it's not easy to bend. So if we can make the steel into a spring, just like a wavy shape, so So this line can be stretched and bent. So we can also extend this to a 3D deformation. For example, we can design the interconnects just like a spring. We can to interconnect the different units by this wavy-like interconnects. So every component unit and the interconnects integrated with the soft substrate. So then the system can be stretched and flexible. So how to make the interconnect just like a spring? So we can learn this from the nature. So for example, for the climbing plants, we know the climbing plants. So the climbing plants can climb itself on the support. So it's the shape of the climbing plants is just like a spring. So we learned this from the nature. We can design the interconnects and the device just like this. So for example, we can design the interconnects of the spring just at the micromillimeter scale. So for example, we can deposit the thin film onto a soft substrate with the wavy shape or just like a grid shape. So then use this. Sorry. So from this, we can just like a climbing plants. So it can be shaped from the 2D and shape it into the 3D. So this is the shape of the 3D. So we can find from this structure transform the deformation. So for this structure, so the interconnects, the electrodes, and the device can be stretched and it's flexible. So from this, the material is the same. The material is inorganic semiconductor or metals, but the device is stretchable. So we are develop some material and fabrication method to transform the conventional 2D to 3D. So now we use this method to fabrication a 3D flexible electrodes for neuroscience. So for example, we develop this flexible electrodes. So this flexible electron can be integrated with the nerves. So the electrodes with the nerves, so it can be climbing automatically climbing onto the nerves, and the interface is robust. So when we deform the stretch the nerve, the electrodes can be tightly onto the nerves. So then we can apply the voltage to stimulate the nerve. For example, we use this to control the heartbeat rhythm. If we apply the voltage, so then we can control the heartbeat rhythm. So we can also integrate the stretchable electrons with the nerve to control the motion. So for example, if we apply the different voltage, so we can control the shake of the legs of the animal. So actually, we can use this 3D flexible electronics to do some more experiments for the neuroscience. And then we can apply the different voltage to control the motion of the body. So now this is a design. So we can also we also want to know how the deformation to influence the semiconductor efficiency. So we have to develop some string engineering for the semiconductor. So we can make the semiconductor material into a very shape. So for the very shape, just like a valley and the peak. So at the valley and the peak, the deformation is different, the strain is different. For example, for the strain of the peak is tensile. However, the strain of the valley is a compressed. So then from this structure, we can to demonstrate how the strain to influence the semiconductor efficiency. So so for the materials, gallium australium. So it's inorganic semiconductor material. So for the very structure with the different deformation, so we can measure the semiconductor properties. So we can find that the very structure with a non-uniform strain can lead to a durable periodic band gap. So that means if we make the semiconductor material into a spring structure, so we can affect the semiconductor properties. So from this, we can design the structure to avoid the deformation. We usually to design the strain isolation approach to enhance the semiconductor properties. So from this design, so we can develop many different kinds of the integrated device. For example, we can develop a flexible electronics with under the semiconductors, so to measure the pulse, measure the heartbeat, and the other motions of our body. So we can also integrate the photoelectronics device and the microelectronics onto the same software substrate. So we can use this to measure the temperature and to measure the light. So, for example, the software substrate is usually by the PDMS or PI. So we can use this technology to develop a temperature sensor and the photo detectors by the silicon. So then we use the transfer printing technology to integrate this different component units onto the software substrate and then package. So then we can get the stretchable and flexible integrated device. So for this device, we can to detect a wide band light from the violet to invisible to visible light and the near infrared frequency. So we can also use this design technology to develop the flexible oximeter. So for this, we can develop a soft photo detector, just like this, and also we also develop the flexible circuits. So these circuits can process the signal and then wirelessly transmit the data to our cell phone. So we design the circuits, and we also use the transfer printing to integrate the different units, and then we can finally get the integrated flexible integrated device. We use this device, we can measure the oximeter. So for example, this is our flexible integrated device. So however, everything we can make it flexible. However, we cannot make the battery flexible. So this is a battery. Okay, so we attach this flexible device onto the wrist. So then we can measure the oxygen saturation, and then we can also measure the pulse. So actually, we use the same approach. We can to develop a bowel sound monitoring patch, the software patch. We can attach this software patch onto our stomach, around our stomach. So this can to monitoring the voice of our bowel. So the bowel sound is very important for digestive system. So we use this, we can attach this patch onto the bowel, so it can be long-term and continuously monitoring the sound of the bowel. So, for example, this is a substrate. This is a sensors, a voice sensors. This is a circuits, the flexible circuits. So from this design, the system, the flexible integrated device can monitor the voice or the bowel sound. So we designed the two units for the voice detector because we have to reduce the friction noise. For example, if we attach this patch, so the clothes will introduce the friction noise. So we use these two methods to can reduce the friction noise. Finally, we can get the bowel sound. So the bowel sound can to monitoring our digest systems. So we can also develop some skin-like integrated device. That means we can make the device very, very thin. For example, we can make the system just about 3 micrometers. So we use this method to a device to monitoring the glucose. So the thickness is only 3.8 micrometers. So it's very, very thin. We can attach this device onto the body to measure the glucose. So it's very for this device. We integrated the glucose oxidase electron deposition catalysis and the conductor onto a very thin soft substrate, and then we attach it onto the body. So when we applied the electric field will drive the glucose out of the vessel, and then the electrical field will drive the glucose onto the surface of the skin, and then we can measure the glucose. So use this method, we can change the monitoring, the glucose testing style. So we also develop a very skin-like integrated device for a long-term continuous blood pressure monitoring based on the PPG principle. So we can measure we can establish the model between the blood pressure and the PPG signal. Finally, we use the flexible photoelectronics under the microelectronics. So then finally we can get the blood pressure. We also use this approach to develop a flexible and stretchable ultrasonic device for simultaneous acoustic energy transfer and communication. We use this to use the ultrasonic as energy, and we also use the ultrasonic as communication. So we fabricated this device, and then we integrated this device with the heart. So this is just like a pacemaker, but this pacemaker without battery, we just use the ultrasonic as the energy, and this pacemaker can use the ultrasonic as a communication. We also use this approach to develop a flexible ultrasonic device for blood velocity monitoring. So we use a Doppler effect. So we just attach this ultrasonic device array onto our neck. So from here, so we can monitoring the blood velocity. So we also compared our results with the commercial device. So the results are almost the same. So this is our design. So we use this approach, we can get a different kinds of the flexible device. So now we want to develop a large-scale manufacturing technology. So if we want to develop the large-scale manufacturing technology, for the chips, we have to develop the technology based on the wafer level technology. So I just introduced this technology. So if we want to make the wafer flexible, we have to thinning the wafer. So from mechanics, the bending stiffness is based on the thickness. So if the thickness is very, very small, so the bending stiffness is very, very small. That means it's very easy to bend. So that this is the principle of how to make the flexible wafers. So based on this approach, we develop a technology to fabricate the unit. For the CMOS process, we can develop the PMOS and NMOS. We use the SOI technology to fabricate the PMOS and NMOS. So finally, we can combine this design with the thinning technology. Finally, we can get the flexible wafers. So this is a fabrication technology for the chips. So for the SOI technology, silicon oxide and the top silicon. So when we fabricate the functional units component by PMOS and NMOS, so finally we can remove the substrate, and then we transfer the units onto the flexible substrate. Finally, we can get the flexible chips. So this is the graph of the chips. So, but during the fabrication, we can find we use the lithography. The lithography leads to a refined feature size about 100 nanometer for the top electronics. So this is the SEM picture of the electronics. So we can measure the electronic weights. So we can give the cross-section picture of the device. So finally, we integrated the units onto a flexible substrate after the package. So then finally we can get the flexible chips. So the flexible chips under the periodical bending, so it's reliable. So from this we can develop how to make the chip flexible. So actually, during this process, the transfer printing is a very powerful technology, and transfer printing is essential for integration of the device. That because every unit, every die, we have to pick the die and pick up the die and then print it onto the flexible substrate. So we have to develop the transfer printing technology to pick up the die. So we develop many kinds of the transfer printing technology. For example, we develop the velocity controlled transfer printing approach. We use the viscoelastic effects. So when you peel the stem very quickly, so the interface strength is great. When the peeling velocity is very low, so the interface strength is low. So we use this effect to control the transfer printing efficiency. So we also design the microstructure of the stamp surface, so that we can tune and control the interface stress. For example, for the stamp, we make the different microstructure. This microstructure is like micro pillars. So we use this micro pillar to tune the interface adhesion. So we also develop some transfer printing by the laser. So we use the laser to heat the local area. So the local area will deform. So then we use this to control the interface strength. So for ultra thin chips, for example, if the chips is about a few micrometers, so if we use the stamp to transfer print, it's very easy to introduce the fraction. So it's very easy to break the chips. So for this kind of ultra thin chips, we develop the liquid transfer printing. We use the liquid, the surface tension, the surface tension of the liquid to control the interface strength. For example, we can put the sample onto the liquid and then use the liquid surface tension to peel off the unit, the component unit, and then we tack it onto the soft substrate. So then finally we can get a very thin. Here we use the droplet to transfer printing. So for the droplet, we use the droplet to pick up the very thin or tiny component, and then the droplet with the objects onto the soft substrate. So when the droplet evaporate, so that the component unit will connect with the soft substrate. So we develop a different transfer printing technology. The different transfer printing technology is for different object size. If we use the stamp, usually the object size is greater than the 10 micrometer. So if we use the laser, So the size is about 1 to 10 micrometers. So if we use the droplet, use the liquid to transfer printing, so the size is usually less than 1 micrometers. So we have to develop the reliability test method to evaluate the reliability. So we also develop some models to analyze and evaluate the interface stress. So we based on the fracture mechanics. So we can develop some models to analyze the fracture mechanism. So finally, we establish the reliability model and the test technology. So now for our current technology, we can integrate the different chips onto a flexible substrate, and then we can conduct the test to evaluate the reliability. So this is a memory device. The flexible memory device. So this device is tested under the cyclic loading. So we can from this it's very stable. It's very robust. So for the dynamic loading with the fixed curvature, so more than 10,000 cycles. So this is a fatigue test. So the chips, the flexible chips, and the circuits is very reliable. So we can also use this method for a high density integration. So we can integrate the 7 layer of the chips. That means we can integrate the 7 micro chips into a one stack. So after the package, so the circuits can work in a liquid nitrogen temperature. So it's a very low temperature. So it's a still work. So for flexible electronics, we established the CMA and the CNAS certification system for the flexible IC. This is the first test system in China to conduct the flexible IC. So we also use this testing approach for the other flexible device. For example, for the flexible OLED, this flexible OLED display can also be tested by the same approach. So we also to develop the wafer level manufacturing process for a large scale manufacturing. So that means we have to thin in the wafers, and then we cutting the wafer into a different die, and then we use a pickup technology to transfer the die onto the substrate, and then package it. So finally, we can get a flexible integrated device or flexible integrated device. So for the thinning technology is very important. So we are developing a diamond nanoparticles for the thinning. So that means we can, for the silicon wafer, so we can use a different diamond nanoparticles to thinning the backside of the silicon wafer. So we can control the thinning velocity and the pressure. So that means from this approach, we can avoid the micro defaults, micro volts during the thinning. So from this, we can also investigate the dislocation or micro cracks during the thinning. So from our technology, we can avoid the dislocation and the crack. Finally, we develop the processing manufacture line of the flexible integrated circuits. From this line, we can fabricate and manufacture the flexible chips or flexible integrated circuits. So this is a flexible wafer. So we use the wafer thinning technology. Now we can produce different types of the flexible and ranging from 4 inches to 12 inches. So here we show a different silicon wafer and silicon carbon wafer. So this is a 4-inch silicon carbon wafer. We can send it into 18 micrometers. This is a 6-inch DC-DC wafers. So the thickness is only 20 micrometers. So it's very flexible. This is an 8-inch wafer. This is a 12-inch wafer. So this wafer is about 20 micrometers. So therefore, we can based on this technology, so we can get different flexible chips. So here is a flexible memories, DRAM, flexible flash, and flexible Wi-Fi chips, and a flexible CIS, and some ADC chips. So this is a flexible FPGA chip. This is actually it's very difficult to manufacture the FPGA chips. Also, we can the flexible other flexible chips. This is a flexible Bluetooth SoC chips. So from this approach, we can we can make most chips into flexible. So we use the flexible chips. We can integrate the flexible chips into a microsystem, or integrated another integrated circuits. For example, this is a flexible data acquisition device or microsystems. This is a flexible wireless route monitoring device. So if we can make the chip flexible, we can make the circuits, we can make the system flexible. So based on this, we are developing many different kinds of the device or systems for biomedical application and the industrial application. So here is a wireless fully implantable micro pump system for transfer and closed loop the management of the body fluids. So the sensor and the controlled system integrated with the soft tubes and the micro pumps. So then these pumps can integrated with the implanted into the body. So we also developed a new luminescent monitoring mode for reactive oxide species in vivo. So we developed this sensor, and this sensor integrated with the micro pump, so then we can to monitoring the reactive oxide species. So we also use this technology to develop some integrated device, so we can integrate the flexible electronics conformally integrated with the heart to ablate with the electrical pulse. So here, so we can find, so the electrodes should be stretchable. So we also use this technology to develop the flexible circuits, integrated the MEMS sensors. So we integrated the MEMS sensors and the flexible circuits into a very, very small tube. So this tube can implanted onto the heart to measure the to measure the heart pressure. So this heart pressure is very important for heart value. So then the heart pressure can be used this micro system transmitted the heart pressure outside to the cell phone. So we use this technology. We also develop some products. So we develop flexible patches. So these patches can measure the temperature and the ECG. So all these products are certificated by the CFD and the CE. So in the COVID pandemic in 2020, so we developed flexible patches, more than 3,000 suits for hospital. So we also use this as a flexible micro system, as a variable system to training the national skiing for Winter Olympics in Beijing. We also use this to develop and some flexible component integrated circuits for IoT, for Internet of Things. So this is a flexible data acquisition microsystems. We integrated different flexible chips onto these circuits. And this circuits can just use as the data acquisition. So for this common component for this device is very light and thin. So that means this data acquisition can be attached and integrated with any equipment. We also use this technology to develop the monitoring system for the routers. For example, the sensors to measure the deform, to measure the stress, to measure the temperature and the vibration with these flexible circuits. And then these circuits can be naturally attached to the routers. So this is a routers testing platform. So when it rotates, so the system can measure the stress, strain, vibration, temperature, and wirelessly transmit this data onto the computer. So we use this to measure the high-speed train. So now we can measure the 500 kilometer per hour velocity. It's the highest velocity test in China. So we can also integrate this rotating system with a subway. So this is used in subway in Hefei. We can use this to monitoring the subway running. If any to test the stress, strain, vibration, and the temperature. So from these parameters, so the office can evaluate the safety and the maintenance of the subway. So we can also use this to monitoring the moment of the transmission shaft in helicopters. So this is very important for the health monitoring test. So this is my talk on the flexible integrated device. Thank you for your attention.
Thank you very much, Professor Feng. This fascinating results and very interesting talk. I'm pretty sure that our panel will have lots of questions to follow up. So now you may just stop sharing your screen, and then I can start to introduce our panels today. So our first panelist is Professor Tsinghua, who is currently working at the School of Precision Instrument and Optoelectronics Engineering in Tianjin University. And also he is the director at the Center of Flexible Wearable Technology in IFET Tsinghua. Professor Huang received his PhD degree in mechanical engineering from Columbia University in 2011, and then worked as a postdoctoral researcher in the University of Illinois at Urbana-Champaign from 2011 to 2014. He then worked as assistant professor in Department of Mechanical Engineering in Missouri University of Science and Technology before returning back to China in 2016. Professor Huang's research area is flexible biomedical electronics, as well as bioresorbable electronics. He has published 85 papers with more than 6,000 citations, and also he obtained 13 authorized patents. Our next panelist is Professor Xiaosheng Zhang, who is a professor at the University of Electronic Science and Technology of China. He received his PhD in microelectronics and solid-state electronics from Peking University in 2014, and then joined EPFL Switzerland as a research assistant, and also served as a research associate at the University of Tokyo, Japan. In 2017, he was awarded the 100 Talent Professorship by the University of Electronic Science and Technology of China. Professor Zhang's research field is MEMS, which covering the micro-nano integrated fabrication technology and its application for smart microsystems. Dr. Zhang has published over 50 peer-reviewed scientific papers, including 2 ESI highly cited paper as first author, 2 books with Wiley and Springer, and also authorized 22 patents. Professor Zhang is also the leading principal investigator leading several national key projects, including NSFC Young Scientist Project, key R&D program of Sichuan province, as well as key projects supported by foundational research funds for Central University. And our ex-challenger tonight is Chuanzhen Zhao from the Stanford University. Chuanzhen is a postdoc researcher currently at Stanford. He worked on developing flexible and stretchable biosensors and bioelectronics in Professor Zhen Bao's lab. And Dr. Zhao did his PhD with Professor Paul Weiss and Professor M. Andrews in UCLA. He co-authored 20 publications in top journals, including Science, ACS Nano, Nanotech Letters, and JACS. His research focused on developing translational bioelectronics, nanolithography, and nanoelectronics. Dr. Zhao has also been awarded numerous awards, including MRS Gold Graduate Student Award, Dimitris Korofesk Foundation Award, and Thomas and Ruth Jacobs Dissertation Award. Now let me introduce inviting all our panelists to the stage tonight. All right, as usual, we would like to first invite everyone on the stage to the stage, and of course, our first question goes to our ex-challenger Chuanzhen. Please go ahead.
Thanks so much, Professor Fu, and thank you so much, Professor Feng, for the wonderful talk. Really learned a lot. It's still up early in California, so it's really great way to start the morning with this fantastic talk. I will start with a more general question at the beginning. So what do you think will be the grand challenge in this field, scientifically and application-wise, like for the flexible electronics moving forward? What do you think we should solve, like fundamental question for science?
Oh, very good question. So from my point, the challenges in flexible electronics, first is a semiconductor material. So if we can develop a new organic semiconductor material, it's the best choice. However, so the limit of the organic material, semiconductor material, I think maybe in a few 10 years, maybe we cannot have a great breakthrough. Mm-hmm. So this is the first. The second challenge, I think, is how to make the flexible electronic device compared to silicon device. It's powerful. Silicon device is very powerful and very cheap. So I think these are two challenges for flexible electronics.
And do you think thank you so much. Do you think moving forward, if we don't, we are here at Stanford working on those type of organic semiconductor, we hope to move the mobility higher and higher, but still we have a long way to go. But if we have to use those hybrid structure per se, and we have to, still use silicon manufacturing, and do you think from that perspective, do we have more challenge from fundamental science, say the mechanical design or the system engineering, or you think we are actually already at the stage we can move forward the technology to more application and mass production?
Yes. I think in the current state, I think the best way to develop the hybrid electronics, just you mentioned. I think for the fundamental science, I think mechanics is very important, because mechanics, I just introduced that we use the mechanics to design, and we use mechanics to develop the reliability test. So, and for the semiconductor physics, I think is also important, very important. So, for example, for my approach, I make the chips, silicon chips, flexible. But now we found, so how the deformation, how the strain to affect the device performance. Actually, there are many fundamental problems. So for the semiconductor physics, we have a theory to analyze the deformation effect on the band gap. However, we don't know how affected the device performance, because the device is very complicated. The device has the channel, so the channel is very important.
Thank you so much.
Thank you.
All right, so thank you, Chuanzhen. So Professor Huang, I have seen you've turned on your unmute yourself. So do you have any question follow up?
Yes, actually, I'm very familiar with Professor Feng. And actually, I have a question, maybe unrelated to the technical aspect of his presentation. Because one of my PhD students showed me a book written by Professor Feng. The book's title is Flexible Electronics Technologies. And he said to me that this is a very good book, and he actually learned a lot of things from the books. So actually, my question is from the standpoint of an educator, because we know that we need more and more people to work in the areas of developing more flexible electronic technologies. So my question is, what should we do in order to inspire more students to get involved into the flexible electronics areas? And say in China, say what can we do to actually help the university to build a system that the student can learn from the cost of flexible electronics? Because to me, it is we need more and more people that can really talented people to work in these areas.
That's very good question. Now, I think we should attract more and more students and more engineers into this field. For the education, I think we can set up a a class for a graduate student and undergraduate students. And now in Tsinghua, I have already set up the class for students. I think we can collaborate each other with a different with the different college, with the different universities to in different universities we can set up this kind of class for students. So the second, I think, is for the book. I think I suggest different scientists and professors can have a book for students. So I just published one book. I think Feng and other professors can publish more books on this area. So the third, I think, it's very important. We can to spread the application or the future applications to attract the students, because the flexible electronics is very powerful. And I think and it's very interesting. I think it can attract students' interest. So and we can give some talk for our professors. We can give a talk for engineering. So so for this, we can attract more and more people into this field.
Okay, thank you.
That's my point.
That's a very interesting topic and question to discuss, I guess, because flexible electronics is such an interdisciplinary field, as we can see that it's really highly requirement of integration of physics, engineering, and also biology, specialists all together. So I guess in the university environment is how to really educate and to provide a platform to train our young researchers and students to actually equip with all this skill together. I guess one of the approach maybe is getting to the labs earlier, so you can pick up the skills, slowly by doing slightly different research project while you're building very strong foundation for science foundation for your major sort of top study topics. Indeed, I think from my personal point of view is that to have those kind of skills takes a long time to build and then to train students to do that. So yeah, it's a very interesting topic and challenge maybe for us to think about how to get students to involve and develop. So Professor Zhang, do you have any questions?
Yes. So thank Professor Feng for the very excellent and wonderful talk. So I have actually two questions. The first one is, we know that for the wearable flexible electronics and as well as for some implantable device, I guess that one the big issues in the development tendencies about the powering, because that I have several work, for example, in this field. So I just wondering that for this kind of the device, for the wearable electronic devices, it's okay, but for the implantable device, I saw that you have a lot of work. It's very attractive work. You try to fabricate some the implantable device and sensors. So how to power in these devices, you think? Yeah, people talk about that. Maybe we can convert the mechanical the energy and as well as the thermal dispensation from the human body, and convert it to be the electricity and to power this kind of the small the devices. Do you think that is makes sense? Or some people talk about it, maybe we should use some the wireless power transmission technology to power this kind of the device. So can you give some comments that the powering technology to support the working of this kind of flexible device or the implantable device?
Good question. In my talk, I introduced our work. I mentioned now I can make every device into flexible. However, I cannot make battery flexible. So especially for the implantable device, now my group focus on the wireless energy transmission. So because for the implantable device, if we want to change the battery, it's very, very difficult. So however, if we use a wireless as the energy transmission, if we use a microwave, so the body can absorb and distract the microwave. So we develop now we use ultrasound as we develop the ultrasound and also the microwave as a transmission used for the transmission, but it's very difficult. So for the ultrasound, the energy efficiency is not enough. For the microwave, so the body will absorb the microwave. So I think a lot of work should be done for this. So energy is always a problem.
Okay. Yeah, thank you so much. So I have very short questions, very, very short questions. You know that if you want to sell story to the people, sell the technology to people, you might to find the very good story, and for the technologies as well. So I just wondering, can you give comments if we, for example, we expect there's some blooming the development of this flexible electronics. What is the killer application you think about for this technology to shock the world and shock the peoples? in which point you think that we will have this kind of the killer application?
It's hard for me to answer this question. If I can know the answer, I will be rich. So, from my point, I think biomedical application should be one choice. But till now, because I only focus on the research. It's hard for me to to say. Design a product.
Let's work together to find the killer application. I guess that is the effective way. Thank you. Thank you so much. Thank you.
Thank you.
I think Professor Feng probably doesn't have this problem selling his products. It's got so many ready over there, like from railway to fast train to COVID clinics. So it's a lot of application there. People can see. Very impressive work. I have a very small question about your transfer printing technique. You mentioned that using that droplet. I suppose that droplet is a water or something, is it?
Yes.
So, and then that's able to do the nanometer to micrometer scale size sort of transfer.
Yes.
So I was just thinking, how could you make sure you have the accuracy in transfer to for the positioning of the transfer?
Yeah, a very good question. For the transfer printing, because our work is from a different thickness of the chips. So if the thickness around is below 1 micrometers, so the device is very thin, so it's very easy to fracture. So if we use the stamp to pick it up, it's very easy to fracture. So that's why we have to develop the liquid transfer printing. So the liquid printing, we use the surface tension to pick up the very thin chiplet. So another difficulty for the liquid is the position. So now in the lab we just use the hand. However, for the chips, we the accuracy is about micrometers, so we cannot use the hand. We have to use the equipment. So now, actually, Professor Huang Xian developed a transfer printing machine for micro LED display. I learned this from Professor Huang Xian. So now my students and postdocs develop equipment especially for the position. Just use this machine for the position.
Right, that's great. So yeah, that's what I got a bit confused by when you say nanometer. It's actually the thickness. That makes sense. Yeah, that's great. Yeah. So any other questions from our panelists?
Yes, actually, I have one question because since Professor Zhang just mentioned the killer application, we saw that Professor Feng actually developed a lot of sensors for industry. For example, using for the wheel, using for the motors monitoring. And do you think there will be a very good chance that the flexible electronics will actually have a lot of development in the areas of industrial sensing, right? Instead of using for the human being, because you know that it is very difficult to persuade people to wear flexible electronics, but it is easier for the machine to wear the flexible electronics device.
Yes. Good suggestion. Yes. So now in my group, we are especially for this years, we take much attention for the industry. Actually, we are develop a few kinds of products for the industry. However, so the market, I think the engineering and the market is needs the education. So the engineering, we need the engineering to accept the flexible electronics. So they like the engineering. From my experience, the engineers like the flexible electronics, but they doubt the reliability and the performance of the flexible electronics. Yeah, I think the education is very important.
Okay.
Very good suggestion.
Yes, I've seen both Chuanzhen and Professor Zhang turn on the microphone. You want to ask more questions?
Yeah, to follow up on that, I think I do my PhD. I work on some flexible electronics for neuroscience, and I do find that all those neuroscientists, they don't really want to work on flexible electronics. They are like, silicon is great, it's very reliable, but I was like, this flexible software, they are better for brain, for the body. They have a better interface, but it's a lot of barrier for them to move from a silicon to something they're not familiar with. They don't know how to handle them. So what do you think we as people who develop the tools, how we can move forward with this barrier to convince people really work on this, and do we need to go from point A to point B instead ask them to go to us? See, use our tools, but do we have to demonstrate that our tool can really be used for the applications?
Good question. Very good question. Actually, this question is hard for me. For example, my group also did some work on the neuroscience. Yes, I think we have the same experience during the research. So, for example, I collaborated this work with the doctors. So, from the doctors, they just need a tool. They just need a tool. He can use it. Just it. So, I don't know how to answer your question exactly. Right. So I just can share my experience. So I think for the flexible electronics, we have to confirm the performance and the way of the usage of the device, and we also need to educate. I mentioned the education again. Right. We need the researchers, the doctors, and engineers accept this kind of technology. I think this is very important. Okay. Otherwise, they can doubt the performance and the performance reliability and the durability, especially for the doctors. Just my point.
I agree. I think going back to Professor Huang's point about education, for students and maybe for researchers or scientists, we can work together with a platform that everyone can get educated. We can get more educated on, biomedical, and they are more interested in bioengineering, and so can combine them together. Maybe that would be a good opportunity there.
Yes, I also suggest. The professors in working in the flexible electronics can give a talk in a different area, in different fields. Yes, right. For biomedical, for doctors, for industry, we can give talks.
That's good. Very good. Thank you.
Thank you.
So I probably just have time for one last short question.
Okay. Actually, I have very small questions. So since today we talk about the flexible integrated circuits, we know that actually there's two technical roles. One is people try to fabricate some transistors by using organic materials to make some kind of they call it the real flexible transistors or the flexible integrated circuit. But there's also some main roles, the technical roles, that people use some substrates, for example, the PI or some other very the solid substrate like paralleling, and as the flexible substrate or the package. But for the functional, the integrated circuits actually is still based on the silicon or some other the semiconductor the common materials. So there's but for this kind of the device, this also can be made to be the flexible. So can you give comment that is the advantage or disadvantage of these two, the technical roles actually? I know that for sensors, maybe people already found a lot of the tools to fabricate these organic sensors and flexible sensors by using the novel materials. But for the integrated circuits, it seems that it's still the main technical roles actually.
Yes. So so I just mentioned that. So for the flexible electronics, there are different stages. So the original stage is organic. because organic is naturally intrinsic flexible. However, the electronic mobility is a big problem. So another bottleneck for the organic is the industry infrastructure. For example, for the semiconductor industry, so the fabrication, the manufacturing is based on CMOS process. So if we use the organic semiconductor, the process is totally different. So that means you have to change the basis of the current industry. So the industry will not use this process. So the cost is very, very high. So I think the best way for current state is still to develop the hybrid electronics. That means we can combine the organic device with the inorganic device. For example, maybe in a near future, we can develop the real flexible cell phone. So now the cell phone's display is flexible. However, the circuits, the chips in cell phone are not flexible. So if we can use the technology I just mentioned, so maybe we can finally make the cell phone real flexible. I think so. For the current, I think the best choice is to develop the hybrid electronics. We can combine organic and inorganic. So this is just my point.
Yeah, thank you.
Thank you very much, Professor Feng. I think that's a great way to wrapping up our talk tonight. With looking forward to see the flexible cell phone developed by your lab very soon. Okay, with that, thank you very much for Professor Feng and also our panel members for excellent talk and also discussion tonight. Now, so what I should do is to we're presenting ICANX talks to present to you, Professor Feng, the certificate for acknowledging your wonderful contribution tonight on this flexible integrated circuits. Our next week ICANX talks will be presented by Professor Sarah Baus from University of Antwerp, talking about 3D characterization of nanomaterials under relevant conditions by electron tomography. So thank you very much, everyone, for joining us tonight, and looking forward to see you in the future on ICANX Talks. Goodbye by now.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。 奇迹。我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can，没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。能够像我一样飞越最高山岗。
来，干杯！走！啊，那盘菜不错的样子啊。
有眼光，我们离开电子元器件啊，都没法生活。
这个电子元器件是哪里产的？
我知道，是太阳药店的。
太阳药店？没听说过呀。
什么？连太阳药店都不知道？我可一直都是太阳药店的粉丝。
要说电子元器件的话，还得是。